Okay, we're going to start. Thanks everyone for coming. This is Jaeger deep dive. We will not do the live demo. I did it yesterday. If you want to see that, go back in time and see that one. Here is more about architecture of Jaeger and how it's deployed and all of the fun, like more technical details that you might want to know. So we will talk about the project briefly as an open source project. We'll talk about how tracing really works. Yesterday I gave a sort of a hand-wavy story about how that's implemented, but today we want to dive a bit deeper on that. And we'll talk about like features of Jaeger and roadmap and all other things. And we'll try to leave a lot more time to Q&A than yesterday. So again, to introduce ourselves, I'm Yuri Shkuro. I work at Uber on observability systems, mostly on tracing. And I maintain Jaeger and OpenTracing and OpenTelemetry. And I published a book on tracing, so if you want to check it out, it has a lot of things that we'll talk about today, but also tracing in general. And Pavol will take from here. Can you introduce?
Yeah, hi, my name is Pavol Loffay. I work as a software engineer at Red Hat. I also work on Jaeger, OpenTracing, and OpenTelemetry projects. So Jaeger is not only a distributed tracing tool, it's also like the whole platform because we provide different bits and pieces which can be used separately. So starting, we have a lot of instrumentation libraries written in different languages. These libraries implement OpenTracing API, and you can use them in your applications to report data to our trace collection backend. And then this trace collection backend writes data to the database, which is later represented in the UI. Then there is also a data mining platform, which can get the data from the database, analyze it, do some aggregation, and stores it back, which is then used in the UI for different visualizations. So Jaeger itself, the architecture is inspired by Google's Dapper system and OpenZipkin. It was initially it started at Uber in 2015, open source in 2017 when it also joined CNCF as incubating project. And last month we graduated as a top-level CNCF project. I would like to thank all of the contributors who made it possible. On the technology stack, the system itself, all the backend components are written in Golang. We support different storage layers, so you can write data to Cassandra, Elasticsearch, Badger, and in memory. The UI is pretty nice. It's written in React. As I mentioned before, there are we have a lot of clients in different languages, so pretty much we support every mainstream language like Golang, Java, Python, Node.js, C++, C#, and there are two community-based PHP and Ruby. Then there is integration with Kafka. We will talk about it a little bit later. And of course, Apache Flink and Apache Spark for data aggregation and data analytics. About the community, so the main repository has about 9,000 stars at the moment. We have a lot of contributors, and at the moment, 15 maintainers across all the projects in the main organization. We are very happy to accept more. We do release roughly every 2 months, although we would like to shorten this time to 1 month to push the features quickly to the community. So it's your part.
Okay. So as I promised, let's talk about how tracing works in practice. This might look a bit complicated, but I'll walk through it. So what we see here in green are two microservices or two services, right? And we want to trace requests between them. And at the top, like left to right and then right to left is the request response chain of like execution going. So what we see here is that when the request comes to the first microservice, it first hits some server endpoint, and there is an instrumentation in that point, which sometimes is called a trace point. Right? That trace point performs certain things. Specifically in this case, it takes the trace context which is typically passed on the wire between those microservices and converts the trace context into some in-memory representation so that when the execution follows to the next trace point and to the next trace point, that trace context, or you can think of trace context like in the simplest form as just a trace ID or a request ID. That's the one that we need to correlate all the events happening within that application, but it's typically more than that. And so that trace context has to be propagated through the whole call chain, not only between the services, but within the services as well, right? So like if you have multiple trace points in the service, they will have to have access to that trace context in order to be able to identify the event correctly. And so what I'm showing here is like a kind of rectangular trace points and circular trace points. The circular ones are, you can think of them as something like inside the application, but maybe it's making a database call, right? So you have a trace point, so you want to, again, capture some information about that database call, maybe like SQL query. And then what every trace point does is essentially, what is a trace point? A trace point is some piece of code which is, it may be in your application directly, or it may be, maybe it's in some framework that your application is using. And that piece of code just gathers the data about the operation that you're about to do. Like I said, like could be a SQL query or maybe some name of that operation. And it writes that data into what I call in this diagram a tracing API, right? It just, you can think of it like similar to login. When you say log.info, you provide a string, you provide some parameters, right? Well, what happens in that case? You actually instrument in your code with the log statement, and that information gets written to some underlying login implementation that runs in your application, which could later on write it to disk, maybe ship it somewhere else. Your application doesn't really care at that point. All you did is like you call like log.info, right? So it's the same thing with tracing. You just have you call a slightly different API. Maybe you start a span and you finish a span. You attach a tag to a span. You give a name to the span. But ultimately, conceptually, it's very similar to just doing a more structured logging. And then tracing API, it's an abstract thing, like similar to login API. There's no like, it doesn't actually do by itself anything. You just call it. It's a callback. And then usually that API is implemented by some tracing library. In this case, it could be Jaeger client. It could be any other tracing library, actually. You can have a Zipkin library, or like with OpenTelemetry, if you go to those talks. So they also sometimes call the SDKs, those libraries. So those libraries, they simply implement the tracing API, and then they do something with that data. In case of, if you take Jaeger client as an SDK, what it will do, it will kind of buffer that data for a while, and then package it, convert it into Thrift format, and send it out of process to either Jaeger, to some of the tracing backend collection mechanisms, which we'll talk about. There are several of them in Jaeger. And then finally, as the request goes further and then your microservice 1 makes a call to microservice 2, the last trace point does something special. It takes that in-memory context, the request ID or whatever, that we kept passing around, and encodes it on the wire so that it has a separate representation on the wire, and so that the next microservice can also like start sending data, because your next microservice may be running in a different process, even different data center, but it will be able to correlate its events or its trace events with the microservice 1, and then as they all coalesce into the tracing backend, eventually we will be able to reconstruct that whole request execution. And so what collection here, like the blue box collection and normalization, because you can have events captured with different instrumentation, like instrumentation evolves over time, sometimes formats change, etc. You may have one application instrumented with Zipkin, another instrumented with Jaeger, third one instrumented with OpenTelemetry. It's actually not that hard to make them all understand each other, and they may all send different data models out of the box, but then collection backend will sort of normalize those into one single model that Jaeger backend understands, and then it will get stored to the database. And from the database, from the storage, we have two paths on the right. Here is like one we basically, all the tracing events are written with a single trace ID as a key, and so you can retrieve them all as a single blob and then visualize them or do whatever you want, like data mine them. So that's conceptually how tracing works. Now, to sort of clarify probably some confusion about Jaeger, OpenTracing, and OpenTelemetry, not only between projects, but between the technologies themselves. So as I was talking through that previous picture, I mentioned there's a tracing API and a tracing SDK, tracing implementation, right? So OpenTracing is that tracing API. If you do something in your application and you make calls to OpenTracing API, nothing is going to happen, right? It's a no-op, basically, unless you actually plug in some SDK with it. And Jaeger is that SDK. Or you can plug in any other SDK or vendor SDK, even custom vendor. And so at the top there, like Pavol told me that it's a bit confusing, but what this really shows is that it's conceptually your application can be instrumented in 3 different ways. On the left, we see is what's called manually instrumented application, was basically, let's say you're not using any framework, you're probably writing in C, I don't know. And so like all the network calls, all the inter-process communications that you're doing, you need to manually go and instrument, and you add the OpenTracing code to that, right? Saying you start a span manually before a call, finish a span afterwards. Typically, no one does that because it's just like everyone uses some frameworks at least, general purpose, right? And so with frameworks, it gets a lot easier because then the instrumentation really needs to exist in the frameworks rather than in your application. So if you have an HTTP framework and you're making a call saying like get something, then most likely you don't need to do anything in your business code which is tracing related, because the framework itself will have some middleware implemented so that the GET request is actually will start a span, finish a span, collect the timing information, and all of that. And finally, on the right, the third option is if you can pull that off, it's like the easiest way to adopt in a large organization where people sometimes use auto-instrumentation, where with the middle box, so even though the framework itself is like instrumented, but the way the instrumentation is typically done for those frameworks is you still need to do some minimal configuration, right? So if you read any OpenTracing tutorials, they will start, okay, well, first instantiate the tracer, then use this HTTP framework, create a middleware for it, pass the tracer to the middleware then will attach to the HTTP framework and start doing its thing, right? So the minimal step that your application still needs to do is create a tracer and pass it to some other frameworks, right? Would be nice if you didn't have to do that, because you can just then deploy tracing without touching any of the application code. And that's what auto-instrumentation does. Historically, like big, long-standing vendors like New Relic, AppDynamics, they provided those auto-instrumentation SDKs where you just, maybe if you're in Java world, you attach a jar to your runtime, and suddenly it goes and like rewrites bytecode in your application and provides this kind of instrumentation. We have at Uber, we're using one library in Python that does that. And it's kind of all my experiences of actually distributing instrumentation to services, that was the easiest one, because we made the change once in one place and every service in Python got the tracing automatically, right? Whereas with other languages, especially with Go, someone needs to do something manual. So those are very all different. And my mic cutting off. Ultimately, all these 3 types of instrumentation, they just talk to a tracing API. And then in that case, it could be OpenTracing API, right? And then the rest is like you have a tracing implementation which implements that API and then collects data and sends it to the backend. Finally, on the right here, you can see OpenTracing icon and then 2 boxes, OpenTracing Contrib and the API. So the API is the actual product of OpenTracing, the libraries that you can use. And then there is a separate organization called Contrib, which was created specifically to create those shared middleware instrumentations that you can use with popular frameworks. Like if you're using Spring or Django in Python, you don't have to keep rewriting everyone the same instrumentation because it's identical everywhere. We can just write it once as an open source project, and then because the only thing that project is exposed is OpenTracing API, you can then plug any vendor, any tracing SDK afterwards, and it will work. So that was the story last year, right? And now we have OpenTelemetry that you've probably heard of a lot. And OpenTelemetry, you can think of it as the next iteration of OpenTracing. It also is a merger with another project, OpenCensus, which was kind of competing with OpenTracing, which was very unfortunate because no one actually wanted that competition. We want the standard way for everyone to instrument rather than everyone have to decide which way to go. And so OpenTelemetry in that sense is very similar to OpenTracing. It has a part which is an API only, right? And you can implement that API yourself or use you can use an SDK which comes by default with OpenTelemetry. Okay, thank you. Hopefully it will be better. One difference between OpenTelemetry and OpenTracing is that OpenTelemetry does come with an SDK, right? So you don't need a Jaeger client anymore. You can just use standard SDK across all board. And all vendors are sort of like join forces and do one single thing, and it will work for everyone. So everything else aside from that is kind of the same. You instrument the code, or you use auto instrumentation, which will talk to that API, and then it will send data through the SDK. Now, another thing that do you want to talk about it, or do you want me? Yeah. So, right, because my mic is not.
Hello. Great. So the sampling is a way how you can control how much data or how much traces are stored in your tracing system. Because if you end up, tracing all the requests, it's just too much data to store. So we have to have a way how to control that. So Jaeger by default does head-based sampling or upfront tracing, which is the way when we start the trace, we decide whether the trace should be stored or not. There are multiple ways how you can decide it, if the trace should be traced or not. There are for example, there is a probabilistic sample which says, I want to store only, 1% of all traces. Then there is a rate limiting, where you say, I want to store only, 10 traces per 1 second. This is all per service, so you can configure it in the service. But sometimes the service has multiple endpoints, and these endpoints have different traffic patterns. So endpoint A may receive, 1,000 requests, and endpoint B receives, 2 requests. What happens if you use probabilistic sampler is that endpoint 2 will get only, very small traces stored for that endpoint. So we have a way how you can overcome this problem by using endpoint level sampling within the service. So you say, for example, endpoint A, which receives a lot of traffic, will sample, 10%, and endpoint B, which receives only, fraction of that, will receive, 50% of the traffic will be sampled. This can be also controlled on the Jaeger server, so you don't have to go to your clients and change the configuration. You just change it in the deployment of the server. On the roadmap, we have also 2 new samplers coming in. There will be a tag matching sampler, which basically means that when you have this trace point, you can you hear me?
Yeah. Not quite.
So.
Yeah, okay, I can continue. So. It was working before. If I speak like this, it might work. One thing I want to mention about the reason why we do sampling in the first place is it's not just because it's too much data, but because it's too much repetitive and useless data, right? Because really, if you think what you use tracing for, you're not using it for monitoring every single request. What you typically use it is for troubleshooting problems. It's an observability tool, it's not a monitoring tool per se. And when you troubleshoot, you actually want to capture requests which have problems, but hopefully in your production, 99% of requests don't have problems, right? And so if you use probabilistic sampling, then you're gonna capture 99% of all your requests that you capture will be, okay, they're fine, they're all the same, they're all successful. There's no reason actually to capture them, that many, right? You might capture like 10 of them in order to just establish the overall flow. And so that's head-based sampling really struggles with that because it makes a decision very at the beginning of the request, has no information about how that trace will look like afterwards, right? And that decision is propagated through so that it's consistent at least, because we don't want to capture like one span here but none of the other ones, right? And that's why the other type of sampling that we're working on is a tail-based sampling, which rather than like a sampling at the beginning, it kind of actually gathers the data anyway, but doesn't store it on disk because it's expensive. It just stores it in memory temporarily. Like most traces only last a couple seconds, so you don't need a lot of memory to keep all of that, right? You can discard all those things within a few seconds. But then once you collect all the spans for a given trace, then you can actually run some basic analysis and say, oh, I see error codes coming in this, like, or I see unusual latencies. I want to capture that. And you may like involve different kind of rules of how you to sample that. And so that part is kind of not too difficult, but there is lots of infrastructure work involved to make this work. So we actually working on rolling this out at Uber, so I'm hoping that it will show up in next year in Jaeger open source. And the tag matching that Pavol was starting to say, that's still an upfront sampling approach, but it allows us to control, to allow like users to change sampling based on specific patterns that they see. So as the name implies, you essentially you push a configuration to the client saying if the span contains this tag with this value, then sample it, right? Or sample it with like a different strategy where maybe higher probability. And so it's very experimental right now. We've implemented it at Uber. We haven't rolled it out in production, but there is one team that's really interested in using it. So I'm curious how that will turn out with this thing. But it's available at least in Node.js and Go clients so far. Okay, so you want to talk about integration, right?
Yeah, I can. So I'm not sure if it works. Okay, so So regarding CNCF projects, we integrate with Kubernetes, of course. We want to make it very easy to deploy Jaeger on Kubernetes. At the moment, there is Jaeger operator, there is the traditional manifests, and there is also the Helm chart. You can, of course, choose one of these which you want to use, which based on your requirement, basically.
What does the operator provide over manifests?
The operator, well, it's not only about deploying Jaeger, but it's also about managing the deployment. So operator will deploy the Jaeger, but then it can also handle the updates, the monitoring, and so on. So it's more advanced. You don't have to understand how to deploy Jaeger to use the operator. You just define, I want to use this storage, I want to use this configuration, and operator will handle all of the deployment for you. But also the upgrades if there is a new version of Jaeger. So by default, Jaeger exposes metrics in Prometheus format. So for example, Jaeger operator, watches these metrics. If there is something wrong, it can, change the deployment accordingly. The OpenTelemetry already ships with Jaeger exporters and Jaeger receiver in the collector. So you can use OpenTelemetry with Jaeger. And Istio and Linkerd already comes with Jaeger as a default tracing system. Envoy also uses Jaeger native client, native C++ client, although you can still use the Zipkin client, which comes by default in Envoy, because Jaeger can receive Zipkin traces. You want to take this one?
Okay. So I guess we didn't mention Kafka, but Jaeger is overall implemented with a push architecture, unlike Prometheus, which uses pull for the metrics. I mean, there are pros and cons to either one of them. So like for us, push architecture was easier because especially the applications need to know very little about how to locate Jaeger components in order to talk to them, right? And the classic architecture, what was originally rolled out at Uber, had a Jaeger client in every application sending data over UDP port to an agent running on a local host, right? You could also run agent as a sidecar. It depends on your tenancy requirements. At Uber, it was easier for us to just run it one single agent per host because we don't have like tenancy requirements. And then the agent then takes care of locating where the rest of the Jaeger backend is, communicating to it and passing the data through. And also the control flow that we mentioned, the sampling strategies, you can configure them on the Jaeger backend, and they become available to the Jaeger clients at runtime. So that's done with the thread feedback loop. I think that only works if you use a agent. You cannot use if you talk directly to collector. And then on the right side, collectors were just like, they were completely stateless, and they were essentially passed through. They would get tracing data and write it to the database as well. And I think we have a next slide for it. So yeah, so the challenges with that synchronous push approach was that if you have a traffic spike in your application, or maybe some application rolled out with a configuration of Jaeger client with like 100% sampling and suddenly starts flooding your backend, there's very little that Jaeger backend could actually do to protect itself with that. That's kind of the downside of the push model. And the only thing it could do is just start dropping data, but because collectors are stateless, there's no partitioning by trace ID. You kind of saying, well, I'm going to drop like 8% of my spans, regardless of which trace they belong to, which means the traces that actually do get through into the database, they have gaps in them, holes, which isn't great. And so what we've done is, should maybe do this slide instead first. What we introduced is a Kafka in the middle. It's supported an open source version of Jaeger, and so in which case the push model still remains, but once the data hits collector, it just writes data to Kafka, and that provided a couple of benefits. One is Kafka is usually a lot more elastic than storage like Cassandra or Elasticsearch, because those are actually they have a schema, they do the indexing, so every write to those storage backends is way more expensive than the simple byte writes to Kafka, right? And so that means that even if there is a traffic spike from the applications, then collectors are still able to keep up with that traffic and actually successfully write it to Kafka. Of course, you can have a spike to such degree that your Kafka blows up, but usually we didn't reach those points, and Kafka at Uber is like super large, so we are at a tiny drop in that. And then we have another component called Jaeger ingester that reads from Kafka and stores data database. It can be deployed in two modes. One is just as a single thing, or you can split it into ingester and indexer. For example, at Uber, we actually split those databases into two clusters so that one cluster stores just the traces that you can retrieve by trace ID, and another cluster stores indexes for those traces and that indexing can lag behind if we want to, or if it happens to be, we don't really care that much. And the second benefit is that we started building the data pipeline on top of that, specifically with streaming Flink jobs. So the previous diagram showed that we had a Spark job. That's the current, it's available on open source. It's a batch job. It reads essentially all of the database for a certain time window, and aggregates data and creates and writes it back to but that's like expensive, especially when you have a lot of data. Then to read the whole thing into Spark is pretty expensive. So it can time out, and you have all kinds of performance issues with it. Whereas Flink streaming just does it all the time and flashes data periodically. And plus, I mean, that's more specific to the Uber, but we also have a standard framework for anything that's in Kafka can be saved to HDFS. So that we can query it with a MapReduce job, so that is like an extra bonus for us at Uber. It's probably easier to set up everywhere else. So, want to talk about Zipkin?
Yeah, if the microphone works.
You might want to hold it.
Yeah. So Jaeger can receive data in Zipkin format. So you can just redirect all the data from Zipkin clients to Jaeger collector. So it can receive the thrift, the protobuf, and the JSON in version 2 format. But then also you can configure Jaeger clients to understand Zipkin context propagation format. So one service can be instrumented with OpenTracing and Jaeger, and other with Zipkin, and they can still continue the same trace. There is also integration with Kafka, which pretty much just uses it gets the Zipkin format from Kafka and stores it into our storage, right? Okay, so new features since basically last KubeCon in Seattle. There is new Jaeger operator. We pretty much it exposes all the configuration what we have in the Jaeger itself, so it's you can do basically everything with it. There is new local storage based on Badger. So this is something like Prometheus, where you have all your data and Jaeger in a single pod. And we also published the storage plugin based on gRPC. At the moment, there are 2 available implementations, one for Couchbase and another for InfluxDB. Yesterday, we talked about graph visualizations, where you can compare 2 traces. This is delayed sampling. We talk about the sampling. This is basically that tag-based sampling. It's not fully open source, right? But it's something we are working on. It will be soon. We made a lot of improvements on the security side of the thing. So you can use TLS with gRPC between Jaeger agent and the collector, but also you can configure TLS between all the storages. This is basically the diagram for the gRPC storage plugin. It's a lot of people ask for it because we don't want to maintain all the storage layers in the main repository. And with this, you can basically have the code base somewhere else, but still use it with the upstream Jaeger. Okay, this is, do you want to talk about this?
I go back. This is something that we didn't mention yet. This is still work in progress. There's actually a bug in the last release, so that's why I didn't want to show it really in a live version, but it will get fixed. It's an easy bug. So what we've been working on is service graphs. We talked about service graphs yesterday, but traditionally those service graphs are based on just single hop relationship between services, right? Which means that you can reason about what your immediate dependencies are for a service, but not beyond that. You cannot, for example, see like if your dependency depends on something else and then depends on something else, can you tell whether you depend on something else or not, especially if you're trying to figure out your SLAs or things like that? You can't really from the single hop diagrams. All you know is that you depend on that guy. Maybe it just replies with the cached result all the time, right? So we started working on what we call like deep dependency diagrams or transitive diagrams, where the diagram is built on the full path that we observed in the traces. And then when you look at it in a graph form, you can actually use like mouse overs and see all the paths going through the services. And in this example, to build that diagram for the full architecture requires some data mining jobs, which is not available on open source yet, but the visualization is available on open source for the search results, because search results is like a small subset of data, which we can already run through that framework. And so you can see here that you can't see it on the screen for some reason. Anyway, there's supposed to be a button right here in the top right corner saying like show as graph. And when you do that, it looks like this. So again, it looks very much like a regular service dependency diagram, but the connections are live and they're sort of sensitive to where you are. And you can focus this diagram on any service. So it's actually oriented to a specific service, right? So it only shows all the paths that come through this service shown in red, not the rest of the Uber architecture. So that mode is like very useful when you're trying to investigate like service dependencies, or we had sometimes scenarios at Uber where people were trying to move services between data centers and they couldn't figure out what their real dependencies are because no one really knows in production. Okay. You want to talk about DCL?
Yeah, and also about this graph, we have a version when you which doesn't require any aggregation job. So basically, when you load the traces in this screen, it will use this data and calculate the graph in the UI, so you don't have to run any Spark jobs. On the roadmap, we are trying to make it easy for data scientists or anybody who wants to play with traces to basically get them, analyze them, and try to find interesting information about what happened. So there are two parts. We want to create a DSL, trace DSL, which makes it very easy to extract features from trace data. And also provide Jupyter notebooks so you can very easily deploy it and play with it, basically. So at the moment, we have some version for Java, which uses Gremlin and extends Gremlin, and that's some very handful methods to navigate within the trace and also to query data between the trace.
Maybe I want to add, the reason for this work is it's a continuation of our data pipeline work. And the reason why we wanted to do this way with a sort of like a generic DSL is really because tracing data is very rich. And it's hard to build tools that automatically extract all that rich information and present it in some way, especially because the use cases for which people want to use the tracing data are often very different. Right, and so Jaeger has some visualizations today that might be useful in some cases, but they're not utilizing like the full power of the tracing data that sits in your database. And also querying for that database from the database directly is actually difficult because there are some questions that you might want to ask that cannot be answered by regular. Whether it's a column or a regular relational database, you can't just express those questions. For example, if your question is, I don't know, I want to know something about like a trace which contains service A colon service B colon service C, right? It's a graph question essentially. But if typical trace storage is implemented either as a key value store or as a relational database, so with relational, when you store one span at a time, there's like you're asking a question about 3 records essentially and their relationship. So you potentially can express it with like nested joins, but it gets really, really ugly. And that's why we wanted to shift towards more like a graph-based DSL like Gremlin, where you get the whole trace in memory and then you can do anything you want with it. You can ask any kind of questions, extract any metric from it. Metric meaning like you calculate something, some feature about this. For example, how much this particular service, what percentage of this service is on a critical path, right? And then the reason we want to do Jupyter Notebook is because developing those kind of programs that extract features, that's pretty advanced usage of tracing. But without having that framework or that capability in place, it's pretty difficult to do otherwise. Like I said, SQL joins is very hard to write for this data. Big MapReduce joins is like difficult. So Facebook had this implementation actually in their internal system, which was very successful, where you can start with a notebook, you can potentially write your query or your feature extraction code over a small data set, which you can iterate and run quickly, and then you get a very good signal from it, hopefully, and then you just take that same thing and you run it against a large volume of data, or maybe you put it in production versus a streaming data, right? And so this is kind of where we want to go, because of course it's a power user tool. I don't expect like regular engineers necessarily go in there, but if you have a dedicated performance engineering performance engineering team whose responsibility is like, okay, well, let's optimize efficiency across the fleet or solve some performance issues in the service, then they would benefit from this greatly, because otherwise tracing data just becomes largely inaccessible with just default visualizations that Jaeger provides. They're only good for certain use cases, but not to extract a lot of rich data.
Yeah, and we would like to also build a community around this, so people would run these aggregation jobs internally and comment whether they find any value in it. And once we prove that this specific job is useful, we can maybe re-implement that and create a very simple deployment without using Jupyter notebooks and so on.
This is basically the same thing as what we've said about the tag matching sampling, is kind of ad hoc sampling where you can allow users to express their sampling policy in more details than just probabilistic or something very simple that we have today. It's more about like, oh, I want to look at these parameters of the trace and make a sampling decision. So that's part of that work. I guess tail-based sampling is what we've discussed before. That's like a larger infrastructure piece that we work in at Uber, so that we can make very intelligent sampling decisions once the whole trace is collected in memory, and then store only the ones that are relevant rather than everything.
With OpenTelemetry, we have a lot of clients in different languages, which takes a lot of time to maintain them. And once the OpenTelemetry is ready, it's production ready, we would like to basically deprecate our clients so we can focus more on these data analytics jobs and provide more features. I think that the data collection should be somehow open sourced and used by maybe different systems. And then Jaeger can focus really on the providing value from this data to the end users rather than just collecting that.
Well, we're out of time, so we can skip that. We kind of talked about it. Yes. I think that's all we have. I don't know. The official time is over, so we can have questions. Maybe people come over here or in the corridor.